Yeah, welcome everybody to my presentation. On behalf of my company, Next Kraftwerke, thank you very much for having this opportunity to speak in front of you, and thank you GIZ, USAID, UK government, and Energy Nautics, and especially the Indian audience for your interest in our expertise. My name is Felix, and I'm working for Next Kraftwerke, which is one of the biggest operator of a virtual power plant. It's a German-based company, and we are aggregating decentralized assets. We have 8,000 of decentralized assets under control, which is an installed capacity of 7 gigawatt. Today I'm going to extract and present to you one particular VPP case study, which is basically one under thousands as being part of this virtual power plant concept. But it's quite interesting because it's combining several use cases you can contribute with VPP technology. And it is about a power-to-gas project together with Greenpeace Energy and the small German city of Hotspot in Germany. So let's get right to it. Some initial words to the company and the two founders. You can see here on the slide. They founded the company in 2009. They made their PhD at the University of Cologne with regards to the German energy transition. And yeah, by the way, 10 years ago, the situation with regards to the energy system was quite comparable to some situations you have nowadays in international markets. So they have been very early with the VPP technology, and that was in the end very lucky because VPP business is about scalability. So yeah, the company now is operating a pool of various technologies, renewable energies we have in the pool, but also loads, power-to-X processes, CHPs, diesel generators, and we are offering ancillary services to 8 different TSO in Europe, so offering a reliable, flexible capacity to stabilize the grid frequency. And also being energy trader, we are off-taker and balance responsible party for PV and wind. So we are the biggest PV energy trader in Germany so far, aggregating 4,000 of PV power plants. So let me draw your attention to this, as I think, very impressive slide. It's so to say the jet stream of the energy world right now. This is something Professor Lenov also paid attention to. We have more or less 4 different main drivers in the energy world, and this is basically the decentralization. So the numbers are based on the German development. So whereas we had 800 more or less conventional central power plants in 1990, we nowadays have 1.5 million decentralized assets. So then we have a liberalized system in Europe, which means that you as energy trader or aggregator, you can act on each energy market as you like. So as you have the certification for being energy trader, you can promote ancillary services on this liberalized system. Then yeah, the digitized world, we can nowadays process millions of signals in a very high frequent way at a low cost. So that leads us as the instrument to set up and contribute digitized energy business and use cases in this world. And then finally, you have this decarbonization, that we come from a system of fossil and nuclear driven system towards a system which is renewable. And this is actually the result of the main driver we've had in Germany, that we're right now operating a digital platform, a technology agnostic platform. We are integrating and interconnecting decentralized assets, having a standard interface in place, which we utilize to establish a bidirectional communication interface to each asset in the pool. And it starts with renewable, wind and PV power plants, but we also have biogas, CHPs in the pool, power-to-X processes, batteries, diesel generators. So we are trying to extract a certain share of flexibility from these assets to promote this flexibility, this aggregated power on the flexibility markets. So this is how it looks like in the reality. This is an insight into our currently operating pool, and each colored point here symbolizing one technology. So you have in yellow the PV power plants, in green the biogas plants, blue is hydro, gray is diesel generators, etc., etc. So we can monitor and steer all these assets spread all over Europe from a central control system, which is running in Cologne in the western part of Germany. We can control all these assets, and if there's a physical issue in the grid, maybe you have an excess of wind electricity in the northern part of Germany, you can then impact this grid positively by ramping down, for example, a biogas plant which is installed in the southern part of Germany. So that's basically the purpose, make decentralized assets steerable and to bring this flexibility as one virtual power plant to the markets. We do not own assets, we are just the man in the middle between the asset owner and the markets. Yeah, with following slides, I want to highlight one project, one asset, basically under thousands, which is quite impressive as an example for the way VPP is generally operating. And we here combine several use cases, ancillary services, but also an access scenario of renewables in the grid. So in general, a fundamental question is when you have a system with a high penetration of renewables, volatile renewables especially, how to deal with a situation when you have very much or a high injection of wind or PV, and you do not consume this electricity on the consumption side because there's the situation of having the surplus of electricity in the grid. So either you can ramp down assets, and curtail assets, that's something what basically significantly happens in Germany. When you drive through the northern parts, you see thousands of ramped down wind turbines because of grid congestions, etc. Or you make use of this, so to say, waste of energy in order to produce hydrogen to be fed into the local natural gas system. And this is basically the project purpose. So we have the city of Hotspot, which is actually facing a surplus of wind energy in its local distribution grid. And they are trying to avoid a power flow in the subordinate grid level, because in the German system you have to pay for it, for the usage of the subordinate grid. So they are facing this problem of having a very big surplus of electricity, and they are trying to transform this electricity, this waste of energy, into hydrogen, because they have a natural gas grid in place, and that's the main purpose. So this is basically the city of Hotspot, the map of the city, which is a very small city consisting of 14,000 inhabitants. It's a typical German city having this one utility in place, which is responsible for gas, electricity, water supply, and also running the distribution grid locally. And this is a scheme of the energy production and consumption. So you have wind turbines, an installed capacity of about 35 megawatt. And then in addition to that, you have about 400 small-scale photovoltaic, rooftop solar, and some big ones. It's about 13 megawatt installed capacity. And against that, it's only 3, depending on the season and the day and the time. You have the consumption of between 3 and 30 megawatt consumption. So you can imagine there are certain situations when you have a lot of a surplus and excess of electricity. And in this project, you have the city of Hotspot, which is basically facing this problem, and then you have the stakeholder Greenpeace Energy, which is offering sustainable gas tariff for its clients. So they are willing or keen to make use of this hydrogen to offer a sustainable green hydrogen gas tariffs to its clients. And then we have Next Kraftwerke, my company, as being part of this project. We are interested in the flexibility of the system, because having an electrolyzer in place, it's a PEM electrolyzer from Siemens, which is very, very flexible, so you can activate this asset very fastly. The ramp speed is very fast. So you can utilize this asset to bring flexibility to the energy markets. So yeah, having this constellation in place, what could be the role of a virtual power plant in this case? Well, on the one hand, we are, so to say, the man in the middle between the asset and the market. So we have liberalized energy markets. We are doing the, so to say, we are creating the value proposition and executing the value proposition on the energy market in terms of energy trades. So you have a certain schedule for the electrolyzer. You have to trade the electricity on the short-term trading market. But also we are promoting ancillary service. So we as VPP operator are certified to offer this ancillary services to the transmission grid operators. But the simple, and on the other hand, there is this technology solution that we have this digital platform and this algorithm, central algorithm as part of the control system, which is calculating set points and an optimized schedule for this asset based on the framework of this excess of electricity locally, but also taking into account price signals from the wholesale market, physical signals from the transmission grid operator, putting all this together and then calculating in a high-performant way under 1 second a set point, a certain set point, to be executed via this bidirectional interfaces on site at the electrolyzer. So what do we need to do this optimization? First thing we need data, and basically we need to forecast some profiles. We need to forecast the PV modules, we need to forecast the wind, we need to forecast the consumption, we also need to forecast price information. So we have several interfaces to market partners, weather data providers externally, we have an API interface, we have this hardware-based interface to the assets to like source availability data, dynamic status data of these assets. We have historical data from the distribution grid operator in terms of the consumption profile. So a lot of data, we have to mix them up and then to calculate the set point. So going through a bit, we start with the forecasting of the PV generation. We have 12 megawatt installed, and it's an individual PV forecasting. And here, to simplify the approach, we are just extracting the largest 3 parks, making an individual forecast for these PVs, and then like mix them up, and then you have in the end, you can see the Morse curve. Here it comes. And then you have this forecast for the PV power plants in overall, and then you have this volatile profile here, which is the real feed-in of the PV portfolio in the city. So what is important here is having this digital platform in place. The initial forecast is based on external weather data and some technical information about the PV power plant, some irradiation angle of the PV power plant, etc. But then to have a very accurate forecast, and that's basically something you have heard in today's morning session, possibly, we can continuously adjust this forecast we have put on the day-ahead market by utilizing the live data. We are sourcing continuously, having this bidirectional communication interface in place. So doing that, we can significantly improve the forecast and then going as close as possible to the real injection of the electricity coming from the PV. Same for forecast of the power generation of wind. We have this 36 megawatt with 4 parks. It's highly volatile. It's much more difficult to predict wind turbines in comparison to PV. And same here, you have some lines here. The blue line is basically the forecast we have done, and then here's the real feed-in of the wind production inside. And then we also have to predict the energy consumption, which is basically very easy approach because it's based on historical data, and the energy consumption is more or less every day the same. You can very precisely predict that. yeah, in the end, we combine all this individual forecast, and this, in the end, is determining the, so to say, the framework for the further optimization of this asset. So that's what we have to fulfill, this excess of electricity in the end. So why do we forecast in the first case as having an impact or an indication for the optimization algorithm, but also we have to trade this forecast on the market to like cover the physical activations with like commercial trades on the markets. Yeah, we have to also forecast the gas grid. We have mainly temperature-driven consumption, seasonal differentiation. We have private consumers and one big industrial side, which is a melting house. And the issue here is that the gas grid has limits in terms of the absorption of hydrogen in the grid. So it's only allowed to inject 5% share of the natural gas as hydrogen. So this is one restriction for us in the optimization, that we say, okay, the algorithm needs to take into account that there's a current gas consumption, and we only can like inject 5% of this consumption into the grid. And then it becomes valuable for the VPP operator, because the system has a gas storage in place, and the gas storage is for us the instrument to extract the flexibility from these assets and to optimize the electrolyzer based on maybe ancillary service markets, but also based on price profiles, volatile price profiles, because we have the framework of the excess of electricity, that in this framework the electrolyzer has to run, and then within this framework we have this gas storage which leads us to make use of this gas storage in order to promote this flexibility. So as you can see here, this is the gas storage capacity, and in this graph you can see the green lines are the operational sectors of the power to gas of the electrolyzer, and in this certain situation the gas storage capacity is full, and then the electrolyzer has to ramp down and finish producing hydrogen. And yeah, this is the result of this optimization, a very simplified approach here. You have the wind injection. This is basically one day or half of a day. The wind production in place, then you have this very stable power consumption, and you have here this typical German PV curve for the photovoltaic production. And the result is then that, yeah, obviously you have here a surplus of electricity. The electrolyzer is working in this period of time. But, and that's the advanced approach in this case study, in addition to this excess scenario, we can also promote this electrolyzer for ancillary services, and this is basically something you can see here. So this is a scenario for the excess. The electrolyzer is running on a certain operation point, and then you have a physical issue in the grid. So the transmission grid operator is demanding capacity to stabilize the grid frequency. So we get this external signal from the grid operator, and then sending out this signal based on the technical restrictions we have with this asset, sending it out and then ramping up the electrolyzer to 1.2 megawatt. And then doing so, we are helping physically to stabilize the grid frequency in the grid, and it's an additional benefit for the asset owner in the end, because he's earning a kind of capacity price by offering this reliable capacity to the grid operators, and we as VPP operator can also benefit from this scenario. So heart of the VPP is, in this case, the optimization in the algorithm, and the algorithm needs to take into account several restrictions. It could be a restriction of the electrolyzer itself, so maybe you have a minimum technical limit, a level you can ramp down or ramp up. You have ramp speeds, which the algorithm has to take into account. You have this forecasts, this excess scenarios, the gas grid capacity, etc. You have wholesale market prices. All this together, the algorithm in the control system is capable to calculate within 1 second. So it's a continuous optimization. And in the end, the result of this optimization of the algorithm is one single set point that will then be sent out to the electrolyzer. And this is a bit the complexity of this case. So we have, avoiding to go to each of these things, but we have some data sources coming from the local grid, coming directly from the assets based on interfaces in place. We also have information about the real energy which is going into the subordinate grid. We have this direct interface via this next box, we call it, which is consisting of a PLC and a GSM modem. And doing so, this is a kind of collector of all this data to be processed in the central control system here. And there, here on the right side, you can see the connection point to the natural gas grid, having the gas storage in place, etc. So this is a very complex approach and very unique as part of the VPP, because here we are combining several use cases, and that's what the digital platform of a virtual power plant is capable to do. Yeah, operating a VPP means you do not have to install a control system to source data and to process data in a high-frequent way. You also need a kind of ecosystem of software and software solutions. So you need an energy trading platform. You need, for each of your customers, kind of client portal. So it's a big and wide ecosystem of different software applications, which is historically grown in our operations. And yeah, nowadays we can also like help third parties to set up and establish this IT infrastructure to run a virtual power plant in the future. Yeah, thank you for your attention, and if you have any questions, please free to answer, to ask anything, and thank you very much.